All right, we can get started now. It's nice to meet you guys. I'm Jackson once again. Past leader is my final semester doing this for Blumling, so kind of sad about that. It's my fifth semester doing pass for him, sixth semester overall being like a TA for him. So hopefully that means I know this material pretty well. Doesn't mean if you ask me something, I might forget or not know. So give me a little bit of grace, but definitely at least for this first unit, first exam, I should be pretty good with my stuff. Um, I would say this first unit that you guys are on right now, maybe not the easiest one, but it is maybe the most straightforward of the entire semester. I think like if you get the idea of how to do this math, you really can't be thrown for a curveball on the exam day. So getting practice like this now, you guys all should be in a good spot in a week from now, I guess. Yeah, a week from now. And this is the format I normally do for these past sessions. So I pull up the worksheet that I made. By the way, do you guys know how to find this? Have you seen yet? If you go over here in Canvas, is like the home page. I got my own little sub page over here. I'm going to post the blank worksheet ahead of time. So if you guys want, you could print it out ahead of time, whatever. Not many people do that, but you could. And then I'll kind of do a split screen and I'll do my work up here. But yeah, anyone have any questions before we get on in? Sweet. All right, so first problem I have up here is I have a couple molecules drawn. This one is drawn with bond line format. This one is more like the Lewis dot structure that you guys saw in Chem 131. By the way, who took Chem 131 last semester? Cool. Who has been a few semesters since then? Cool. All right. Chem 131 is a good class to have some memory of, but really, this is very different from that class. There's like you can count them on your hand the number of times you need to remember something from that class. So don't worry if it's been a while, or even if like it was last semester, but you already forgot the stuff. You'll be all right. So the first thing I'm asking here is what is the strongest IMF that these two molecules have in common? Anyone want to say what an IMF is? Intermolecular force. Yeah, inter meaning between different ones, so not within the same molecule. And it's a force that is not a direct bond between them. So it's not like these lines that are connecting, showing bonded atoms. It's going to be the bonds between all these molecules when you have like, I think of like a bucket. If you dumped a ton of these into a bucket, they're going to still be interacting with the separate molecules. And so you have to think, what is going to be the intermolecular force that these feel? What is the weakest intermolecular force that all molecules have? London dispersion forces, van der Waals forces. Technically, those are not the two exact same things, but you can kind of think of them interchangeably, I think, for this course. So yeah, dispersion forces, and that's going to be between any bond. What's the next one, kind of, that you think of? Dipole-dipole. What defines a dipole-dipole interaction? Polar. Yeah, anything polar. And so really for this class and for almost all of them, a non-polar bond is either going to be something bonded to itself. So if you had like something like that, that would be non-polar, or carbon bonded to a hydrogen. Everything else is going to be polar. So is this polar? Yeah. Is this polar? Yes. Is this part of the molecule polar? No. So then with that in mind, there's one more that we can go a step further. Hydrogen bond. Yeah. And even though the word bond is in that name, it's another intermolecular force. And there's a certain rule. Does anyone know the type of bond that needs to be present to have hydrogen bonding? N, O, or F? Yep. Bonded to what? Bonded to a hydrogen. Yep. And so both of these have that. I like to think of the periodic table. It's like the last three of that, top group towards the halogens. And yeah, and basically that's a really, really strong, you can think of a hydrogen bond as being like so polar that it's almost creating something way stronger than a dipole-dipole. So that would be the answer to this one. These both have hydrogen bonding. Cool. Next one. This is using a little bit of vocab that you might see on a quiz. I don't know if this was in your PowerPoint. Yeah. Yes. Great question. So I kind of went quick over that. Anytime you see that, fun pop quiz, how many carbons are in this molecule that I drew? 4. Yep. You got one here, you got one here, you got one here, you got one here. And then this is going to take some counting. So don't worry if you don't get it right away. If it focuses, how many hydrogens do we think are on this molecule? 10. Yep. So octet rule always applies to carbon. It needs to follow the octet rule. And so you have implied hydrogens. So this guy here has three. So that way it has four bonds. This one and this one only have two. And then this guy has three as well. So that's the way we do like shorthand notation. Anyone in this class going to have to go on to Orgo? A couple of you. I love Orgo. Don't let people scare you away from it. Probably my favorite class I've taken here. So that's a good intro to Orgo. But let's go to the next one. Which of the following pairs of solvents could be considered immiscible? So there's two words here that um, might throw you for a bit of a loop. First, the word solvent. If we're talking a solute and solvent, what is the liquid part? What's the dissolved part? Yes, like I said liquid. Most of the time you think of a liquid. It could be, you can say anywhere. How's it going? It could be a gas or something like that. But, and then immiscible. Have you guys seen that word yet? Well, what does that mean? Don't mix. Yep. Kind of sounds like it too. Um, and so a theme in this class that you're going to see all throughout the semester, all the way up until the final, like one of the biggest things to take home is that like dissolves like. And that means that two things with like or alike intermolecular forces are going to like one another. They're going to dissolve well. So based on that, we have a lot of molecules here. Which pair do we think is not going to like one another? Any guesses? A, B, C, or D? Can you guys see it all right? Also, cool. Well, we can start with this first one. We have, funny enough, the molecule that I drew right here. I didn't plan for that, but that's called butane. And then this molecule would look like this. We have three carbons this time, and then an OH branching off. This is ethanol, or no, sorry, not ethanol, propanol. And what do we think? Would this and this behave nicely together? No, because what is the strongest intermolecular force that this has? Dispersion forces, and this one, hydrogen bonding. So there we go. That's the answer, A. I'll go real quick through the other ones. Both of these guys are going to be dispersion forces. They're both nonpolar. These are both going to have hydrogen bonding. And then this is kind of a weird example. I don't know if it's a great one, but these would both have dipole-dipole. All right. I only say that because this is technically a strong acid, and you'll get to that in a little bit, but this would break off into separate ions, and then you'd have ions to deal with whatever. All right, next one. Yeah, acids and bases are going to be its own unit. It's my favorite unit in the semester. I think it's like the third one. Um, he's probably using that to like have say a fun fact almost. I would go through and it would not hurt to rememorize those six strong acids and strong bases. But I'm trying to think of like how that would be applied to this unit, and I don't see it. So yeah. All right, next one. Which molecule would have the lowest boiling point? So right off the bat, all of these have the same intermolecular forces. They're all carbohydrins, is what we call those, carbohydrates. And so we know it's all going to be dispersion forces, but they differ in their length. So they are either really long, like down here, this is 9 carbons, and this one is only 3. So what do we think the answer is for that one? C. Yep. What makes you think that? Yeah, exactly. So basically, if you have something like this, I kind of think about a lot of these together. They have a lot of grooves where they can have those dispersion forces and they can kind of be tighter together. Whereas this, it's not going to be as strong. So yeah, lowest boiling point is going to be the one that's smallest. This would be whatever this is would be like the highest boiling point. All right, next one. Let's get into some math stuff. So if you guys have a calculator on you, now's a good time to grab it. I strongly recommend using this exact calculator for this class. Sometimes people, their biggest problem they have throughout the semester is that they don't know how to use their calculator. And when we get a little bit further, we do have equations where you need to use the E button, the ln, log, that sort of thing. So don't worry if you forget that from math, but at least you need to be able to confidently press it into your calculator. Okay, so this is what you guys did, I think, in your snow day. Okay, how are you doing? Feel free to take a seat anywhere. So what we do here is we're talking all about concentration units. So you have something like a salt or a solute, you put it into a liquid. We need ways to define that. So there's molarity, there's molality. You guys learned about mole fraction. You learned about mass percent. Uh, maybe even another I'm forgetting, but you need to be able to be comfortable with all of those and going from one to the other. So you might be given a molarity, asked to find a molality, or you might be given a weight and asked to find a mole fraction or something like that. So with that in mind, we have a solution that is made of 3.0 grams of sodium chloride in 150 grams of water with a total volume of 184 milliliters. And I've given you the molar mass here. On the exams, I don't know for sure if you're given the molar mass. Do you guys all remember kind of how to do that from Chem 131? How to calculate that? Cool. You look at the periodic table, count it using the weights. So this first part is saying what's the concentration in units of molarity. Somebody want to say what molarity means? What units those are? Moles per liter, and this is where you gotta be pretty specific. Moles of what per liter of what? Yeah, moles of solute over liters of solution. And I only say that because the next one, molality, if you said moles over kilograms, that would not be the same thing. It's moles of solute over kilograms of solvent. So you do have to be careful with exactly what these moles and liters and stuff are for. Not these ones. So I'll try to be good this semester about saying like this is given to you, this is not, because at this point I think I know them all. Um, all of these concentration units you got to memorize. So I would make like a little table. Flashcards are a great way to do that. But yeah, spend a few minutes working on this first one. If you finish it, go to the next one. And then if you feel stuck, don't worry about it. I'll go through it, both of them up here. Also, for those who came in a little bit late, we haven't done a whole lot, but the recording will be in Canvas. Anyone get an answer for that first part, A? 2.77. I think you might have a like scientific notation error because you got the numbers right, but the decimal not right. So you're really close. So what I got is first step, we take the grams of our solute, that's sodium chloride, use the molar mass, go from grams to moles. Um, that's some Chem 131 stuff. But then molarity, again, is moles of solute over liters of solution. We're told the liters of the solution, it's 184 milliliters. We got to turn that from mils to liters. So all you got to do is put a decimal here. Um, and I got 0.279 molarity. Cool. And then I went ahead and did molality as well. And so for this one, we already got the first part done, right? It's the same numerator, moles of solute. Now we need the denominator, and I kind of wrote this one easy for you guys. I already gave it to you, 150 grams of water. That's our solvent. And so we're going to put 0.150 kilograms, and that got me 0.342. Any questions with those two? Yeah.
One, I think the phrase, like, not afraid, but like,
Mhm.
and then third mission, the one with the interaction, like the stuff that people use, like.
Sig figs. Good thing to think about. He will never try to throw you off by sig figs. So the exams are going to be all multiple choice. You never have to type in answers. It's going to be on a computer. And so he wouldn't give you like 0.342 and 0.34200 or something. So don't worry about it. It's a good thing to be aware of though. And you're right, for adding and subtracting, that's based on the decimal. So the least amount of points after the decimal is what you go based off of, and multiplying and dividing. It's overall sig figs. You go by the least total sig figs. If anyone does want a review on that, I now do have that because I took analytical chem last semester. It was a stupid class, but I did learn sig figs again because I had forgotten them. But don't worry about that. All right, next one. What is the mole fraction of a 200-gram aqueous solution? What does aqueous mean? Watery, wet, water. With a 29.2 gram of sodium chloride, I gave you the molar mass again, dissolved within it. What is mole fraction? Yeah, I think I get what you're saying. So yeah, moles of the solute over moles of the entire thing. So moles of the solution. You got it. So spend a few minutes working on this one. I think this one's a little bit trickier, um, but I'll go over it up here. Yeah, the last one I gave I'll give that one like a 2.5 out of 5 for difficulty. This one's more like a 3.5 to a 4. So if this one's giving you some trouble, don't worry. I also failed to give you the molar mass of something that you need for this one, and that's the molar mass of water. So molar mass of water is 18.02 grams per mole. That's a good one to memorize, though. Yeah.
For moles of aqueous and penicillin.
Moles of the solute over, you got the denominator right. The numerator is only the sodium chloride. Yeah. Mhm. All right, anyone get an answer for this one? Yeah. 0431. I got a slightly different answer. So I think you might have missed the final step. Um, so there's a good number of parts to this one. Getting the numerator shouldn't be that tricky. Again, we're going from grams to moles with the molar mass. So we got that part. Now we need to make sure that we're getting the moles of both the water and the moles of our solute in a separate way. We can't use the same factor. We can't use the same molar mass because water and sodium chloride have different molar masses. So we need to subtract the amount of solute that we have in grams from the overall grams of the solution. And that gets, so 200 minus 29.2 gives us 170.8 grams of our solvent by itself. And then we can go from the solvent's mass to its moles of water using the 18.02. So this is moles water. And then the last step, which maybe where you guys missed, is that we still have this as the numerator, but we need to make the denominator the moles of both the water plus the moles of our solute again. Does that make sense? Cool, because moles of solute over moles of the entire solution, so we need both parts. And so I got 0.0501.
Why we subtracted?
29.2?
Yeah.
Yeah. So we need to find the moles of both components. So we need to get the moles of water and the moles of our solute, sodium chloride. And to find the amount of water present, we can go from, yes, so we need to get rid of the sodium chloride. Whatever's left, we know that's only our water. So we have a mass of the water. We can go to moles of the water, and then we can find, by adding the moles of the water and moles of the sodium chloride, the moles of the whole thing. This one, definitely tricky. I mean, this last step here is not the most intuitive. It takes some time. Any other questions about that one? Cool. All right, next one. Calculate the molarity of a 14% solution. So it might say percent mass on your exam. It might simply say percent. If you see percent, think percent mass. Um, percent mass of sodium chloride, and I've given you the density. So the density, grams per centimeters cubed. And then I gave you a little conversion. 1 centimeter cubed is always equal to 1 milliliter. So again, this one's pretty tricky. I kind of made your guys's this past session, the first two past sessions is what it normally would be because you guys had the snow day. This is my first time seeing you all. So, and I do have work at 7. So if we don't get through the whole thing, I'll push some of these to the past session on Sunday. Hopefully we can though. But give this one a try. This one takes a few minutes as well. I wanted to give you guys a lot of practice with the concentration stuff because I know that's what you missed with the snow day. Yeah, you could totally expect things like this. With He has a little bit more conceptual stuff than what I put in because I think conceptual stuff I can try to help you, but reading it is really the best way that you guys can get it. I try to give you a lot of the math, and really, if Chem 131 was a lot of concepts, Chem 132 is math. So it's not complex math. You don't have to be too scared, but like definitely if you are shaky with your algebra, you're gonna get some extra practice with that this semester. But yeah, it would be like this, and they're all multiple choice, probably like 20 to 25 questions. So what is percent mass, by the way, real quick? It's the same exact thing as mole fraction. Yeah, grams of solute over grams of the whole solution. So same exact thing as mole fraction, but instead of moles, we're using grams. So a mass unit. And that is very important because on these types of problems, you have to make a certain approximation that you maybe, I'm sure he talked about in the videos. Again, don't worry about that, but it would be 14 by itself. Yeah. But yeah, you really never ever need to know that for this class. And unless, is anyone here a chemistry student? Then you guys are good. Your days of sig figs are behind you, I think. Yeah, I'll work through it with you guys. Great question. This one is again, if the last one was a 4 out of 5, this one might be as hard as these will get. So, um, he might have said this to you in the videos. I'm guessing he did, but it might have been confusing. When we have a mass percent, we need to use a certain approximation to even get anywhere because it feels like, what do I do? Where do I start? 14% by mass is the same way as saying for every 14 grams of our solute, we have 100 grams of the entire solution. So now that we have this, we have some numbers that we can work with. So I'll always mass percent, turn it straight into whatever that mass percent is over 100 grams of the solution. So then we can take this in 14 grams, use that molar mass, get moles of our solute. There's the numerator. So we got one part down. And now this next part's a bit trickier, but we need to now find liters of what for molarity? Close. Solution. Yeah. Molality is where solvent is in the denominator. Molarity, we want solution. So we have 100 grams of solution, but that's in a mass unit, not a volume unit. To go from mass to volume, we need density. And so we can use that now, these 100 grams of our solution, and basically flip the density upside down as a unit conversion. So 100 grams, using the train tracks or whatever they called them in 131, we can go 1 centimeter cubed for every 2.16 grams, because we know we have to cancel out numerator and the denominator. And then centimeter cube is 1 to 1, so you don't really need to write this, but if it helps, you can. And then look at that, we have volume, and then the last step is we need it in liters. So again, I always do this in my head, but you can also write this out. 1 liter for every 1,000 milliliters. And then after that, we have a denominator. So 0.2396 divided by, this ends up getting me 0.0463 roughly liters for the solution. And I got a molarity of 5.17. And if you ever are doing this and I get an answer that's like 0.01 or 0.02 off from you, he also will never, I'm guessing he will never give you answers that are that close. So don't worry about a small rounding error. Do you guys feel good about that one? Nice. All right, now let's go on to what you guys did in person yesterday. So we talked about something called a Van't Hoff factor. Basically, that's a way of saying that when you put a polyatomic ion or a complex compound or whatever into solution, it breaks apart into a certain equal number of ions. So what is the Van't Hoff factor of calcium nitrate? And this is an instance of like where I said there's a handful of times to remember stuff from Chem 131. This is one of those, like 1 of 5. So calcium nitrate, I made this one purposefully a little bit tricky. I didn't write out the chemical, what is it, like compound formula for you guys. So you need to be able to look at the periodic table and write what calcium nitrate is. And nitrate is one of those polyatomic ions that you sadly do need to memorize. I don't know if he would do this on your test, but I'm doing this to kind of help remind you guys. Anyone have a guess? 2, your guess? 3's your guess? All right, let's do it. I have to do this real quick, and I can't do it off the top of my head. But calcium is going to have what ionic charge? +2. Yeah, if you're looking at the periodic table, it's in that second column. Those are going to be +2. So we know it's calcium 2 plus, and then nitrate. Anyone remember what that ion looks like? NO3 minus. Yep. So there's a few ways you can do this. The way I was taught is you take this guy, toss it over here. That's a terrible arrow. Take this guy and toss it over here. So when we write this all together, we get calcium NO3 in parentheses, and it gets a 2 there. So 3 is the right answer. So when we break this up, we will get a calcium 2 plus, basically what I wrote up here, plus two nitrate ions. So one that we don't write here, plus the two here, so three. All right. What's the Van Hoff factor of the molecule to the right? This is benzene, uh, cyclohexane that has three double bonds in it. Benzene, if you do take orgo, is a very, very important molecule, aromatic compound. What do we think? One. Yeah. What makes you think the Van Hoff is one? Non-electrolyte. Yep. Non-electrolyte, only carbons and hydrogens. Those are all non-polar bonds. It's gonna, you put a, you get a bucket of benzene, all these molecules are gonna stay looking exactly like this. They're not gonna break up. Cool. So now we're getting into using that Van Hoff factor for something, and this is the osmotic pressure. Has he talked to you guys about this? Okay, cool. Want to make sure. Osmotic pressure is a formula that I think is given to you. I have it memorized only because I've been doing this. It looks like a pi symbol is equal to, um, I write it as CIRT, but C is concentration and it's always going to be molarity. So MIRT, whatever you want. R is always given to you, it's gas constant. And the entire semester, we're going to be using temperature. Don't ever use Celsius, pretty much, except for like the next thing we're going to do. Everything else is Kelvin the rest of the semester. So get used to converting from Celsius to Kelvin. Anyone know what that conversion is? Yeah, Celsius plus 273.15 if you want. So spend a few minutes working on this. I'm asking what the osmotic pressure is in units of atmosphere, given this concentration of calcium chloride at 22 degrees Celsius. And R, there's two gas constants you'll have to know for this test. The one that we're using is 0.08 821. Forget it.
That's never like that, or that.
That's always given to you. 0.8, yeah, 0.821. I'll cut it off there. Four sounds right though. And the way your formula sheet will have both of the gas constants, and the way that you can know you need to use this is because the units of this guy, and I don't worry about all the other stuff, but somewhere in there you're going to see the word atmospheres, osmotic pressure, atmosphere. That's what you need to remember. So this you're using this guy. A little bit later in the semester, you'll use the other one, but it'll make sense then. So I'll work this one out with you guys. I gave you the molarity. That's nice. It makes it easy. What's the Van Hoff of calcium chloride? This is kind of the hardest part of this problem. Three again. Yep. Calcium, again, is a 2 plus. And chloride, what's that ionic charge? -1, because it's in the seventh halogen. Not halogen, sorry. It's in, I forget that stuff. But it's going to break up into two chlorides for every one calcium. So three goes here. I gave you the gas constant. And then 22 plus 273.15 is 295.15. Cool. So multiply all that into your calculator. 2.54 atmospheres is what I got. Anyone want to briefly explain what they think osmotic pressure means?
Is it, like, when it's, like, the solubility and then how much it forces it to, like, stop, it gets to, like, a point, like, the water to, like, stop.
Yeah. Yeah, exactly. So we have a solution. Think of a bucket. If it's got a lot of solute in it, and you've maybe heard the term semi-permeable membrane, either in this class or in a bio class. If we can let liquid through this little line here, but not solute, if this guy only has a little bit solute, we're going to shoot as much water over to this side to balance it out and hit a homeostatic level. Is anyone here pre-med, pre-A, whatever? Pre-PA? Okay, awesome. You guys will learn a lot about osmosis if you haven't already in a bio class. And then if you get to like animal phase or human phase or whatever, you talk a lot about nephrology, the kidneys, and all that stuff. And knowing homeostasis and osmosis is super important. And then also for pre-med folks, osmotic pressure is like on the MCAT. It's a good thing to know for all cellular stuff. So kind of a good thing to keep in mind. Okay, two more. Good. It looks like we'll get out at a good hour. What is the boiling point in Celsius? So this is one of those few times where the answer is going to end up in Celsius. Of an aqueous solution containing 13 grams of K2SO4, potassium sulfate. Sulfate, again, another one of those polyatomic ions. There's not too many, but nitrate, sulfate, those types of things. In 200 grams of water. And I gave you the boiling constant for this problem. And also, if you ever had a freezing point depression problem, you're always given the boiling constant and the freezing constant. Cool. Spend a few minutes working on this one.
Mm. Oh, oh, SO4 is it a two negative?
Mhm. Yep. All right, cool. I'll start working on it up here with you all. This is a formula I don't think you're given. I would memorize it as if you're not given it. It's possible it's on the exam, but that's going to be the delta T for the boiling point elevation and freezing point depression. So always remember when we add a solute, the boiling point is going up and the freezing point is going down. So it's basically creating a bigger difference between those two. This is not Q equals MCAT. This is the delta T equals Van Hoff factor times molality. So that's going to be the italicized M times the KB, the boiling point constant, this one. And then a very easy mistake people make, I'll get to at the end of this problem. But so we know this is what we're working on. We've added K2SO4, that's a solute. So we're going to be increasing that boiling point. Van Hoff factor, what do we think that is for K2SO4? 3, let me see. I think you're right. Going to break up into K plus. So we're going to put 2 of those there for every SO4 2 minus. So yeah, we have an invisible 1 here and the 2 here. So Van Hoff is going to be 3. And then the molality, this is the hardest part of this problem. We're given the grams of that solute. So we can go from grams to moles using that molar mass. So I won't even write that one out. So 13 divided by 174.26 is equal to 0.0746 moles of that solute. And then again, what is the denominator of molality? Kilograms of solvent, exactly. And I kind of made it a little bit easy on this one. I gave you the grams of the solvent, so 0.2 kilograms because it's 200 grams. So that molality is going to be 0.373. And then you're always given that constant in the problem itself. Let's multiply those together.
Like, is the 0.373 that you got for the long?
Yes, that's what I got. Is that what you guys got? I think I did it right. Should just be 13 grams going to moles, and then divide it by kilograms of water, so 0.2. Because this is where you always have to be looking at the wording of the problem. So it's not going to be the same method for every one of these problems. In this one, let's go up a little bit. The one where we did have to do that, I believe it was this one. I gave you the grams of the entire solution. So if we wanted to find the solvent by itself, we have to go solution minus the solute to get solvent. On this one, I made it to be honest, a bit easier for you, I gave you straight up the grams of only the solvent. That's a really good question. So that's why that's going to be zero point 0.2 in the denominator. And then overall for this delta T boiling point, I got 0.571. Would that be the answer to this problem? No, why not? Exactly. Yep, we have to find out what the new boiling point is. So boiling point in Celsius, 100 degrees Celsius, it's always going to be plus whatever we got there if it's boiling. So the answer would be 100.571 degrees Celsius.
But
For the delta T part, because again, the way this problem is worded, I didn't ask you what's the delta T. I asked you what is the new boiling point. So if I'm asking you what the new boiling point is or the new freezing point, we have to think about what we found from the delta T and either add it if it's boiling or subtract it if it's freezing.
so that's about it if it's boiling past the freezing.
Not divide, add if it's boiling, subtract if it's freezing. So if you're boiling water on a pot and you add some salt, you do that for a few reasons. It tastes good, but you can make it so the boiling point of that water goes up. Same reason he was talking about in class, you salt the roads before it freezes overnight. And that's because you do that, the freezing point around that area is going to drop a little bit. So instead of freezing right at 32, those sidewalks might freeze more at like 25 degrees Fahrenheit, you know? So you want to add salt to lower the freezing point and raise the boiling point.
And then where did you get the 100 pieces to add on to it?
That's so anytime it's boiling point, the boiling point of water is 100 degrees Celsius and the freezing point of water is 0 degrees Celsius. That's why Celsius, yeah, 0. Celsius makes way more sense than Fahrenheit. 0 and 100 are good numbers. 32 and 212 are weird numbers. So cool. Those are all very good questions. Last one here. This one I think is going back to concentration stuff. So this is again more from the snow day. What mass of calcium hydroxide must dissolve in 850 mils to make a 2.4 molarity solution? We'll spend a few minutes working on this one. So I didn't give you the molar mass of this one, so let me give that to you real quick. Calcium hydroxide, which by the way looks like this, because calcium was the 2 plus. Molar mass is 74.09 grams per mole. So this one I would go back and say is more like a 2.5 out of 5 difficulty. But it might feel weird because we did a lot of the hard stuff and now we're going back. And honestly, that's what trips me up the most is like going back to the easy stuff after you've done the hard stuff. I forget where to start. So in order, I took him for Chem 131 my first semester here as a freshman. So I kind of don't fully remember what they look like, but um, yeah, I don't know. I bet if you asked him, he would tell you straight up. Or the other TAs, they'd be better to ask because they've taken him more recently for this class. But yeah, so what do we have here? We have two numbers, so we got to use at least one of them to start with. And I think it's going to be easier to start with the last one. So we have 2.4 molarity. So we know that that means we have 2.04 moles of that calcium hydroxide for every liter of solution. So let's try to get, I mean, we're asked for a mass of calcium hydroxide. So let's go from moles of this to mass. So that's not bad. Um, or no, let's do volume first because that's going to be easier. We can get rid of liters entirely. We don't want them in our final answer. Let's let's throw them away. And so the way we can do that is use the volume given to us. We want to make an 850 milliliter solution. So if we use 0.85 liters, we can cancel out volume units. And then that's great because we're left with moles of calcium hydroxide by itself. So we have 2.04 moles once we have the volume that we really want. And then from there, all we're using is the molar mass to go from moles to a mass unit. And that's it. So sometimes with these problems, it can be overwhelming trying to think of where to start. It doesn't hurt to start somewhere. You know, always try something and then you'll get a vibe of like, this feels wrong. Throw it away. Try something different. With this one, at first, I thought I was going to do using this with molar mass straight up. Felt wrong. I remembered, okay, let's get rid of volume. Then we have only one thing. It won't even be a unit conversion. It'll be a unit number by itself. And that's easier to work with. So again, the final answer here, something like 151 grams. Yeah, does anyone have any questions about that or anything else from this past session? This one ran a little bit long. Sometimes they're more like 30 minutes. So don't feel like you need to block off a full hour of your day every time for these. But yeah, I'm glad you guys came. Hopefully it was a little bit helpful.